Hello and welcome back to Differential Equations section 3.5 on non-homogeneous equations and undetermined coefficients, and today variational parameters, which is also in the same 3.5 lecture. Now this is the part 2 of undetermined coefficients, and we're just going to add later on variational parameters to the lecture. Before we go through the variation, let's work one or two examples of undetermined coefficients, because we have defined undetermined coefficients and we did some of the exercises, but you know it's a longer procedure, so let's see a little bit more of that. Now what we've seen before is these are the constant coefficient equations of literally whatever degree. So they can be 4th and 5th and 10th degree, but they have the forcing term on the right-hand side. And that forcing term could be polynomial, trigonometric, exponential, combinations of all of those, as we are going to see. So we have to then follow the instructions and deal. If we run into repetition, we have to deal with the repetition. That's usually the biggest problem, the biggest issue that we run into as we go through this. So let's work out some of the examples to refresh undetermined coefficients and then jump into variational parameters. These problems are long and painful, but such is life, right? During the break, I have something really cool to show you, so I hope you guys are gonna stick around. Let's see. Any problem with initial conditions? Let's see how well the 34 is gonna go. Y double prime plus y equals to cosine x, and then y of 0 is 1 and y prime of 0 is -1. So y prime of 0 is, let me just verify, so y double prime plus equals the cosine x, and then y prime of 0 is equal to 1 and y prime of 0 is equal to -1. Okay, I like this. All right, so now what is our problem? We have a problem and we are supposed to solve y double prime plus y equal to 0, the homogeneous part first, and we know that this is going to give us that r squared plus 1 equal to 0, from where r is going to work out to be plus minus I, which gives us that complementary solution of c1 cosine x plus c2 sine x. And this is now the situation where when you realize that your f of x, we had it before as f of t, but right, you can have it as x as well, is cosine x, there is a repetition, right? So we have to choose for our yp, we have to choose x cosine x. We can't choose cosine x because cosine x would be repetition. Same thing like with e, right? When you have e to the 2x and e to the 2x, you pick up x e to the 2x in the repetition. And now you just take a whole bunch of derivatives here and see what you get. So your yp prime is going to be, now you have a product rule, right? So copy the first, derivative of the second, plus copy the second, derivative of the first is just 1. And then y p double prime is copy the first derivative of the second plus copy the second derivative of the first, so that's going to be negative cosine, no, copy the second negative sine x, there we go, and then plus derivative of cosine is minus cosine x. No, minus sine x, what I'm talking about. There we go. So one more time, we have to do the product rule here. So derivative of the first, copy the first derivative of the second, which is cosine x, and then copy the second derivative of the first, derivative of negative x is negative 1, there was a plus there, so now it's a minus, and derivative of cosine is negative sine. Okay, we have all of that done. Now, if you just carefully look at the form of your yp, these are supposed to be f's. So you have the form of your yp now is you have a cosine x, you have a negative 2 sine x, so you can say a sine x plus b cosine x plus c x cosine x plus d x sine x. We have x sine x, we have x cosine x, we have a single cosine, a single sine, so we actually have 4 of these now. And what we do is we take 2 derivatives of this, which is going to be a huge mess, and then just use the second derivative and yp in the original problem, equaling it to cosine x to come up with the coefficients for a, b, c, and d. All right, so let's go. Y prime, more product rule and stuff. Derivative of sine is cosine, so this just becomes a cosine x minus b sine x plus c and then the product rule plus d and then the product rule. So the product rule is copy the first derivative of the second plus copy the second derivative of the first. I kicked c outside. Same thing for the second one. Copy the first derivative of the second, so that's just going to be x cosine x. Then copy the second derivative of the first. It is good practice to simplify this. Now we are going to have more terms, and what you could do is you can distribute these c and d constants, so it's less mess. You do not have to factor cosine and sine. I mean, you could, but there's no need. So a cosine x minus b sine x minus cx sine x plus c cosine x plus d x cosine x plus d sine x. There we go. One more derivative, because we do need the yp double prime to plug into the differential equation. So negative a sine x, that's a basic derivative, minus b cosine x, that's a basic derivative, minus c, there's a product rule here, minus c sine x, plus d, there's a product rule there, and then finally plus d cosine x. So that's our second derivative. I just need to go back and do the 2 product rules. So copy the first derivative of the second plus copy the second, and derivative of x is 1. Now go to the other one, copy the first derivative of the second, so minus x sine x, plus copy the second cosine x, derivative of the first is 1. There we go. All right, our equation to plug all of this mess in was y double prime plus y equals cosine x. So we have y double prime and we have y. So need to plug those two in and see what we get at the end. So yp, y double prime, right? So that's negative a sine x minus b cosine x minus cx cosine x minus c sine x minus c sine x minus dx sine x plus d cosine x and plus d cosine x. So all of that stuff that I wrote so far is just y double prime. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. It's good to do this check. Now, you know what? I'm going to change this plus into the orange plus. There we go. So we know that now that's a plus, and now we need p. That's a sine x, b cosine x, a sine x plus b cosine x plus cx cosine x plus cx cosine x plus dx sine x equal to cosine x. There we go. Awesome. All right, so now factor out all of the sines, all of the cosines, all of the x sines, and all of the x cosines, get their coefficients in a parenthesis. So sine x is going to have what? This term, this term. I'm just looking for vanilla sines. This one, this is a vanilla sine. And when I say vanilla sine, meaning there is no x sine x, it's just sine x. So I have negative a. Maybe I can, since I used the red there, negative a, negative c, positive a. There we go. Then plus cosine x, that's going to be blues. This is a vanilla cosine, another vanilla cosine, another vanilla cosine, another vanilla cosine. That's going to be minus b plus d plus d plus b. Then we have plus, let's go with x sine x. So those, let's go with green, I guess. X sine x is this puppy here, and this one here. Well, they just cancel. Minus d plus d. Oh, fine. And then we have plus x cosine x. Those can be rainbow. X cosine x, x cosine x. That's a minus c plus c. Equal to cosine x. So, what do I have now as the equation? Coefficients a are cancelled, negative 2c sine x. B's are done, plus 2d cosine x. And these terms are just gone because they're multiplied by 0. Equals to cosine x. From here, I see that negative 2c is equal to 0 because there is no sign on this side. And that 2d is equal to 1. So c equals to 0 and d equals to 0. I think that's good. No, d equals to half. What am I talking about? There we go. D equals to a half. So now, good. Now, you might say, well, what's happening with A and B? Well, A and B you guys already have in this solution. That's your A, that's your B. It's a large confusion for a lot of people. They said, well, what happened with my A and B? Well, remember that you had, they look the same, right? And they were gone out of calculation, right? Because they cancel out, but they are still represented with a C1 and C2, which we are going to compute using these. So that's a good part right there. Still works. So now, what is the overall solution for the problem? It is y equals C1 cosine x plus C2 sine x. That's technically your A and your B from before. And you just have plus 1/2 for D. So you go into YP and look which term has a D in it. This is the one, x sine x. X sine x. There we go. Now, your job is to work out the initial conditions. Y of 0 equals 1, y prime of 0 equals -1. Well, we need a y prime. That's going to be quick. Negative C1 sine x plus C2 cosine x plus 1/2 of the product rule. Copy the first derivative of the second, so that's x cosine x, and then plus 1/2 sine x. Derivative of x is 1. Okay, and now we just plug these values and we compute. So I have y is equal to 1 equals to cosine of 0 is 1, so C1 survives. Sine dies and the other sign dies when you plug x equals 0. Good. So we got that the C1 is 1. Now for the second one, -1 is equal to sine 0 dies out, right? Sine of 0 is 0. C2 survives. And then this term dies because x is equal to 0. So it's like half times 0 times 1. So it's 0. And this term dies because sine of 0 is 0. So we just got C2 equals -1 instantly without any calculation, which is awesome. I have my solution. Y of x is C1 is at 1. So it's cosine x minus sine x plus 1/2 x sine x. There it is. So undetermined coefficients at its finest, right? And we had the repetition. This time repetition was on cosine, and right, it all worked out. Let's see another example, and then switch to variational parameters. Variational parameters will not have any theory to it. There will be a formula which you memorize, and you just plug stuff in, and you go from there.
Professor?
Yes.
I noticed in this problem that if you had just used YC as Y complementary to find C1 and C2, you would have gotten the same C1 and C2. Is that just the case for this problem, or is that always going to be the case?
Because it's always the case because it's A and B, right?
Right.
From our undetermined coefficients. Yes.
Cool. Thank you.
You're welcome. But again, it's only when it's repetition. You're not going to have that when there's no repetition. So it's like, you know, just working 1,000 of these problems. It all falls into place. I know it's not, you know, too encouraging when I say just do 1,000 of these problems, but it's actually that. 2000 problems. All right, let's take a look at a higher degree problem. Maybe something that, I think this looks bad. 14 looks bad enough. It says y to the fourth derivative of y minus 2y double prime plus y is equal to x e to the x. So let's go and take a look at this problem. We have our, here we go. So we have our differential equation, the homogeneous case with the fourth degree. And when I put that's going to be r to the 4 minus 2r squared plus 1 equal to 0. Now, if you studied algebra, you would know that this compresses into r squared minus 1 squared, right? And then you have r squared, which is r squared equals to 1. So r is plus minus 1, but each one of those is multiplicity 2. So you have r1 equals r2 equals 1, and r3 equals r4 equals negative 1, let's say. You already have repetition in your chapter 3, right? Chapter 3.1 solution. So now when you write this yc, it has to be c1 e to the x. Was it x or t or x? Right? You know, on this side, if they use t's, it's in terms of t's. If they use x, it's in terms of x. So c1 e to the x plus c2x e to the x, right? Because you have repetition. And then you have plus c3 e to the negative x plus c4 x e to the negative x because of repetition. So we haven't even started undetermined coefficients, and we already have a living nightmare over here. Now, when you look at your f of x, your f of x is x e to the x. And that is repetition right there. So you have to bump that up into an x squared. Let me put that in blood. There we go. Now, I'll point the arrow at it, and I will say, because x e to the x is repeated, so we need, obviously, the next order of x as x squared. All right. Woohoo. Let's go. Derivatives. So f prime of x is going to be copy the first, derivative of the second, plus copy the second, derivative of the first. And then the second derivative is, again, the same thing. So it's going to be x squared is x plus 2x e to the x plus the derivative of this. Copy the first, derivative of the second, plus copy the second, derivative of the first. When you put all of these together into your yp, what do you have? You have a vanilla e. You can call it a e to the x. You have the single degree x, so that's going to be plus bx e to the x. And then you have your x squared thing plus cx squared e to the x. And now you take those derivatives, and guys, you have to take 4 derivatives now. Oh, I forgot a constant. Because if I take the next derivative, oh no, what am I talking about? No, 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 no. This is e to the x. That never goes to 0. Forget I said anything. I haven't said anything. All right, so now let's take the derivatives. A e to the x plus copy the first, derivative of the second, plus copy the second derivative of the first, the bex, plus copy the first derivative of the second, plus copy the second derivative of the first. Awesome. We have to go to the fourth derivative here because it was y to the. I know. It is my fault. I picked the problem. So I kind of. I don't want to do the problem. I don't want to live now. E to the x plus copy the first derivative of the second plus copy the second derivative of the first plus derivative of this one plus cx squared e to the x plus 2cx e to the x plus, and down derivative of this, copy the first 2cx derivative of the second plus and then plus copy the second derivative of the first is just 2c e to the x. I have to factor this. I mean, there is no way that we are going to take these derivatives in this form because the product rules are piling up with each one, and I still have to take the third and then the fourth derivative. So I am done with this nonsense, and I'm just factoring out e to the x because I just want one product rule. So when I factor e to the x, what do I have? I have what are my e to the x's, right? It's this one is a vanilla, this one is a vanilla, this one is the vanilla, and this one, right? So I have a plus b plus 2b. So a plus 2b plus 2c. And then we have plus x times, and then coefficients with that one are the blue. So this one, this one, this one. So that's b plus 4c. And then plus x squared is just the 1 is x squared. So that's just c, x squared. So now when I'm doing the product rule, I just have one product rule. Otherwise, I would have 1, 2, 3, 4 product rules to deal with, and then that would just make a mess again for the next derivative. I don't want to do that. So the triple derivative now is copy the first, and then, guys, this is just a polynomial. You take the derivative of this like nothing. So copy the first derivative of the polynomial. Well, these are all numbers. That's the derivative is 0. This is x, so derivative is just b plus 4c. And then the derivative of this one is plus 2cx. So that's our derivative there. Plus copy all of this mess, and derivative of e to the x stays e to the x. So we have this, and then copy the same a plus 2b plus 2c plus x, kill me now, b plus 4c plus cx squared. Who picked this problem? Now, factor e to the x and combine the two parentheses, so we have again one product rule for going into the fourth derivative. So e to the x, and now the two parentheses come together. That means I am adding constants, I am adding coefficients of x, and then I just have that one x squared. So let's write cx squared first. Then my x terms are b plus 6c, b plus 6c, because I have two c's over here, four c's over here. That's a 6c plus b, and then times x. And then I have this constant over here at the end, plus a plus 3b plus 6c, a plus 3b plus 6c. I mean, there has to be an algebraic error somewhere over here. It's just too annoying. Fourth degree. Copy the first, derivative of the second, 2cx plus b plus 6c, plus copy the parenthesis times derivative of e to the x is still e to the x, and then times the parenthesis cx squared plus b plus 6c x plus a plus 3b plus 6c. Awesome. Now, what are the ones I need? I need this one, I need this one, and I need the vanilla one, yp, this one. And they go here, here, and here. And then equal to the forcing term. So it's a little bit busy, right? So if I factor out again e to the x and mush the two parentheses together, I have cx squared plus b plus 8c times x plus a plus 4b plus 12c. So this is your y fourth power minus 2 times y of the second power, which was e to the x. I don't need the parenthesis here. E to the x, and now the parenthesis. Now let's find that factored y double prime. So that's the red and blue. A plus, so let's start cx squared. Then the blue term was b plus 4c. And then we had plus, was it a, 2b, 2c, plus a plus 2b plus 2c, and finally plus our yp, which was this. We have, if you factor out e to the x again, in parentheses, what's left? A plus bx plus cx squared. Cx squared plus bx plus a. All of that equal a e to the x. There we go. Oh, yes. Yes. Factor out your e to the x, divide by e to the x, they all drop. E to the x cannot be 0. When you divide e to the x to both sides, they are gone. Now, you just need to go through this arithmetic to get your constants, your x's and your x squares on a pile, and compare it to the other side, which says 0x squared plus 1x plus 0, right? That's what x means. No x squares, no constants, and just 1x. So all I need to do now is to collect x squares on a pile, x's on a pile, constants on a pile, and compare it to x on the other side. I'll have my coefficients. So what do I have here? And I just hope that all of these, that arithmetic and derivatives went well before, because a single tiny mistake anywhere will not cancel the terms, and we're just going to get all of these values we don't need. So if you notice, this term, and this term cancel, because you have positive cx, and then a negative 2cx squared, right? So they cancel. So we don't have to worry about those. Let's worry about x terms. So for my x terms, I have b plus 8c from the first parenthesis minus 2 times b plus 4c from the second parenthesis, and then plus b from the third parenthesis, and all of that stuff is going to be equal to 1. And finally, the constant term, it's the first parenthesis is a plus 4b plus 12c minus 2 times the constant term from here is a plus 2b plus 2c, and then finally plus the constant term from the third one is just plus a, and that needs to be equal to 0. I'm not crying, you're crying. B's are gone. Something is wrong. Something is wrong, because as you can see, they all canceled here, and I just have 0 equals 1 in this one. Yeah, some arithmetic somewhere went wrong, and look what I got. So all of the constants, I hope you see, that they all cancel without multiplying all this out. This b plus this b is 2b minus 2b is 0, and then 4 times negative 2 is negative 8c. There are no a's, and I'm getting 0 equals to 1, and we know that's wrong. So arithmetic is wrong, and as you can see, after writing all of this, yeah, good luck to find it. Chances are you're not going to. It's literally start from scratch, which we don't have time for. I have to move on with this one. I will encourage you to go and do this problem step by step. Make sure that I took the derivatives correctly. So you take the derivatives and go through it. So we have our x squared over here now. Copy that derivative e to the x, z to the x, and then 2x here. And if you keep taking the f triple prime and f to the fourth, fourth derivative here, you will not find any new type of terms. They will just be recycling these ones. So I know this is good, but then derivatives after that and collecting the terms and factoring terms, there is going to be, later on we introduce minus signs and everything else. So there is a mistake somewhere. So this is definitely no bueno. This is the line that is supposed to give us a value, because that's the only one that has, right, x is the one that is listed on the forcing side, on the forcing term. So that line has to give us a equals something, or b equals something, or c equals something, and the other ones are going to fall off the truck. Please redo this problem. I have to abandon this because we have to go through variational parameters and then have the review, because exam is coming up. It is arithmetic mistake somewhere with these basic derivatives and things. So you either find it or or ignore the problem. I mean, I don't know what to say. We can do this maybe at some other time, but it's just a waste of 30 minutes. Variation of parameters. That's the last part for the lecture. Then we're going to take a short break, and then if you are joined on Zoom, obviously you are the part of the review. So, variation of parameters. What you are supposed to do here is memorize this one formula which calculates the YP. So you are not going through this procedure. As you can see, it can be very interesting. What you're supposed to do is this. It's a very simple formula, in my never humble opinion. Very simple to remember and to memorize. And then, you know, the question is, are you good with integration? Forgot my dx over here. There we go. So this is the variation of parameters formula. And look how easy it is to remember this. Whatever function is in front, the other one is inside. And you have the forcing term, which is the right-hand side, divided by the Wronskian. There is nothing special about this formula, because the things that you know is that your YC is C1Y1 plus C2Y2. Well, there's your, you know, your Y1, and then your Y1 will also go into Wronskian. So the Wronskian of X is Y1, Y2, Y1 prime, Y2 prime. So all of this is very simple to set up, and the formula is ridiculously easy to remember, because, as I said, whatever function from C1 is outside, the other one is inside the integral, and you always have f divided by the Wronskian. So the formula is a joke, and you can just crank this into, right? Now, obviously, there is a limitation to this method, right? Because that's only y1 and y2. Can we do our y to the 4 problem from before, the fourth derivative? No, you can't. Or the triple, or, you know, the fifth, or whatever. It doesn't work with variational parameters. So variational parameters is a nice little shortcut with a cute formula. It's very easy to remember this formula. When you go out, you can just leave this behind, written on like a napkin or something. Just leave it casually behind. Let the others wonder, like, what the hell is this? I do that sometimes just for fun, because I'm a terrible person, right? And then you just go from there. Let me pick up the problem from homework. So variational parameters, they list 47 through 56. No, 47 through 57 problems, and they say try. I mean, literally any. Ooh, let's do one of these. We haven't had anyone with hyperbolics. I don't want to discriminate against hyperbolics. So let's go this equals to sine hyperbolic of 2x. There we go. So this is your problem 50. We haven't had hyperbolic functions yet. It's not nice, right? So what do we do? Well, as always, we solve the homogeneous case first, and that's your R business. And what you come up here with is your value for R squared is plus minus 2. Now, what that gives you over here, what that gives you is that YC solution of C1 e to the 2x plus C2 e to the negative 2x. And hello Y1 and Y2. All you need to do now is to plug all of this stuff into your Wronski, into the formula, and just plow through calculations. So now, what's the Wronski? It's going to be e to the 2x, e to the negative 2x, 2e to the 2x, and negative 2e to the negative 2x when you do the derivatives. And that's going to be equal to, right? We do it this way. So you have negative 2, because e to the 2x minus 2x is 0, e to the 0 is 1. And then you have minus, and then when you do the other diagonal, you also get another 2, so the whole thing is negative 4. And you know that your f of x is sine hyperbolic 2x. So now, just stuff all of this into the variational parameters formula, which is a joke. Negative y1, okay, integral y2, okay, times sine hyperbolic of 2x, okay, divided by the Wronskian, negative 4 dx, plus the second y2 is e to the negative 2x. Since you put y2 outside, y1 goes inside, times sine hyperbolic 2x over negative 4 dx. And all you need to do is to integrate this, and you're done. All right, so what's yp? Yp is going to be e to the 2x over 4. And now you have your integral e to the negative 2x sine hyperbolic 2x minus e to the negative 2x over 4, and then integral of e to the 2x sine hyperbolic 2x dx. So what's $1 million move to integrate something like this? Well, if you spent more than 6 minutes awake in Calc 2, you know that sine hyperbolic, let's put something, or I don't want to use x, sine hyperbolic m, whatever, is equal to e to the m minus e to the minus m over 2. And the reason why I didn't want to use x is because if m is 2x, then these are 2x's. That's why I didn't want to use 2x in a formula. So now, let m be 2x, and your integrals become the biggest joke ever. E to the 2x over 4, integral of e to the negative 2x. Oh, the half, sorry. The half goes out as an 8, this half. So e to the x times e to the 2x minus e to the minus 2x dx, and then minus e to the minus 2x over 8, and then the same e to the 2x, and you have e to the 2x minus e to the minus 2x dx. Hyperbolic functions are absolute blessing to work with. So what do you have? E to the 2x over 8 integral. When you distribute this, it becomes a 1, right? Because it's just e to the 0. So it's 1 minus e to the minus 4x, because minus 2x, right, when you add them, is negative 4x dx. That's a joke to integrate. And the second one is another joke. This time you have e to the 4x minus 1. So we can just integrate this real quick and get what? X. And then this would give us the denominator of 4, but also a minus, so plus e to the minus 4x over 4. Yep. And then minus over here e to the negative 2x over 8. And then we have e to the 4x over 4 minus x. You distribute the ones in front. More algebra. So that becomes e to the 2x times x over 8 plus e to the minus 2x over 8 times 4 is 32 minus e to the 2x over 32 minus and minus makes a plus x e to the negative 2x over 8. Now, obviously, when you can flex, you should flex. These two combine together, and these two combine together. And factor out everything so you can leave the form for your hyperbolics. So if we start with a 32, I'm going to factor out 1 over 16. And that leaves me with, negative 1 over 16, because I need a positive to be listed first. So that's e to the 2x over 2. Well, I can put over 2 for the whole thing. Minus e to the minus 2x over 2. There we go. So that's the first one. And then for the second one, I am factoring out x over 4. And that leaves me with e to the 2x plus e to the minus 2x over 2. So if you factor those, negative 1 over 16 sine hyperbolic 2x plus x over 4 cosine hyperbolic 2x. We could have used undetermined coefficients as well, but this is way cooler. And now you have your solution of yp. So of y. It was c1 e to the 2x plus c2 e to the minus 2x and minus 1 over 16 sine hyperbolic 2x plus, if you want to put this as 1/4 x cosine hyperbolic 2x, you can. No one will stop you to make it look pretty. Or you can just put x over a quarter, x over 4, I mean. And that's it. Now, some of you might immediately scratch their head and say, well, doesn't this look like sine hyperbolic almost? Because the sine hyperbolic x was e to the x plus minus e to the minus x over 2. Doesn't that look like that? Or cosine hyperbolic with a plus, right? And the answer is yes. You can write this as a combination of hyperbolics. which actually in many books is presented that way rather than this E business. So you quickly figure out that you live in this dual world where the problems of this form, let's say, give you sine hyperbolic / cosine hyperbolic stuff, and the problems of this nature, which end up being complex, give you sine and cosine world. So this can be written as hyperbolics, as the C1 cosine hyperbolic 2x and plus C2 sine hyperbolic 2x. Now, not every book focuses on that. Those of you that are interested in mathematics obviously will explore that option and see the world with different eyes, because then you can maybe do this and combine it with it and have less calculations left in your answer and so on. So all of that stuff is obviously for those who are interested in, right? Those who are not trying to pass the course. It's for those who are learning the course, because they understand that everything we learned here pops up later. And I just hope that you guys are going to stick around for your for the break. Okay, that's variational parameters. I would label that as a joke, because the equation is a joke to remember. Yeah, it does have a lot of algebra, but undetermined coefficients have it too. You know, pick your poison. Now, undetermined coefficients work for every order of the equation, the third degree and the fourth degree, right, when you have a fourth derivative and so on, where the variational parameters only works when you have a second order, because there is only y1 and y2. Remember that the amount of these solutions here is the same as the order of the equation. So if you have a third degree equation with a third derivative, then you also have a y3. Well, there's no y3 in the formula, so you can't use it, right? You can't use variational parameters for that particular one. But if you have a second order constant coefficients and you don't want to mess with, you know, repetition or all of these kind of things, it already, this formula accounts for all of that, and it gives you the answer immediately. So you could go back, not for this problem, which I gave up on because I made a mistake somewhere, but already for this problem, which was a lot of work anyway, you can go ahead and use your variational parameters on problem 34. That will be an amazing exercise for you to do at home if you really want to study and learn this stuff. And go ahead, get the same answer we have at the end. Your, after everything, you should be here. And then go ahead and compute your C1 and C2, right? And so on. Remember, your undetermined coefficients and your variational parameters only gives you this, right? And this part is the part from 3.1 and 3.3, which was that R equation, right? For the characteristic equation for the homogeneous part of, non-homogeneous part with constant coefficients. And the extra term is the one that you do undetermined coefficients or variational parameters, right? So it's one of those two. When it's a second degree, you can do both. When it's a third degree, fourth degree, and so on, you are stuck with undetermined coefficients and 10 hours of work, right, at that point. That concludes 3.5. The next lecture is 3.6, forced oscillations and resonance, for us to take this into mechanical vibrations. So we can study what happens when you have forcing introduced into the system as well. And then that will, in 3.7 later, become electrical circuits. So we are left with other 3 sections for chapter 3. Very few sections in next chapter. We'll be ready for the next exam very quickly, within, let's say, 2 weeks or so. So please don't let your guard down, especially, don't miss classes after the exam. And I'm really concerned that some people are missing today's class and lecture because they don't want to confuse or whatever it is, with the exam coming up. It's just all differential equations. I mean, if I include this on the test coming up on midterm, I said I won't, but if I include it, it will stop being confused instantly. It's amazing how easy it is to flip the switch between confusing and non-confusing in these courses. You just say, oh, that's going to be on a test immediately. Okay, it's not confusing anymore. Now I got to study it. I don't understand why it would be confusing to study this, even if it's not on an exam. Eventually it will be on an exam. And who cares about the exam? Garbage. No one cares about the exam. You need to know this stuff. Which transitions us to our break. So those of you interested in review, you better connect on Zoom, and we're going to go through whatever problems you need to live. We'll resume YouTube on Wednesday with 3.6 with mechanical vibrations, forced mechanical vibrations.